In school mathematics, a lot of the attention always goes to content standards, but I think even more important than that are the standards for mathematical practice, the ways that we think about, make sense of, communicate, and interact with each other mathematically. So what I want to do in this video is just give some of my thoughts about each of the standards for mathematical practice from the Common Core State Standards, and just briefly share what they mean to me or some thoughts that I have about each one. So let's start with the first standard for mathematical practice, which is problem solving, or more formally, make sense of problems and persevere in solving them. So this is the big problem solving standard for mathematical practice, which is a big part of mathematics. Tackling problems is what a lot of people love about mathematics. And here the way that I think about it is I really contrast problems and problem solving as different from exercises or just completing skill and drill kind of practice. So problems means you are tackling something where you have some knowledge to build on, but you have not actually been shown how to solve this exact problem before. It's something that you have to actually figure out, or the students have to decide how to tackle the problem, how to approach it. They'll have to also decide if they've gotten a correct answer and that sort of thing. If students have been shown how to solve it, then that's not really a problem. That's more of what I would call an exercise, and many people call exercises. So here in problem solving, we really are talking about students being able to roll up their sleeves, make sense of a problem, figure out how to approach it, try it out, see if it's working, adjust their approach if they have to, all that problem solving kind of process. And that's where the perseverance comes in as well. If you are having to figure out how to solve this thing that you've not seen before, then sometimes that means you persevere, and that's an important part of the practice. Number 2 is reason abstractly and quantitatively. So as you can tell, this kind of has two parts. The abstract reasoning part is about contextualizing mathematical ideas, so taking something that's kind of an abstract math idea and be able to put it into a context, think about what it means in a kind of a situation, but also decontextualizing, so see a situation and pull out the abstract mathematics from it. I actually tend to think about that process of contextualizing and decontextualizing more in line with the practice 4, which we'll get to in a second, about modeling. So for me with practice 2, I think more about the second part of it, which is quantitative reasoning. So quantitative reasoning is something that we want students to develop. This means having coherent representations of mathematical ideas. It means having some sort of sense-making or meaning attached to values. So they're not just meaningless symbols on the paper, but we have meaning to them. Also, it means quantitative reasoning, students understand magnitudes, they understand units, and they also understand kind of how to estimate in reasonable ways. Practice 3 is one of my favorite practices, one of the most important ones in my opinion, and this is construct viable arguments and critique the reasoning of others. So this is really about providing justifications for your ideas, being able to construct a logical argument, and this sort of thinking, careful thinking with logic, with reasons, I think this is one of the things that mathematics can really help students develop, and it's one of the reasons that mathematics, I think, is important for the world and for citizenship and that sort of thing, is we can help students recognize bad logic, a bad argument, or a flawed argument, and we can also help them recognize a valid argument, or an argument that's based on good premises and with a good, kind of conclusion. So I think that's really important. I think also things like critiquing other people's arguments in a respectful way, where you're not attacking the person, but you can critique or point to holes or the need for clarification in their ideas. I think that's something that we do need in the world. We need people to be able to do that sort of thing, and students to get better and better at that. One of the things that's also my favorite part of this practice is identifying hidden assumptions. So somebody might put forth an argument, and it's a good practice mathematically to be able to say, wait a minute, you have an implicit assumption here that you haven't stated, and maybe it's important for us to pull those out. I think that's important in mathematics and also can be important in the world. So this one, there's a lot to dig into. At all grade levels, students can be giving reasons, giving justifications, and they can also think about whether they're convinced, whether they see flaws in other people's reasoning in a respectful way. The fourth practice is model with mathematics. And the main thing I want to say about this one is just that model with mathematics does not mean what some people mean when they use the word model. This practice is not about modeling mathematical ideas. So like using base 10 blocks to model the place value, or to use a graph to model a function. Model with mathematics as practice is really about using mathematics to model something from outside mathematics. Maybe it's something from the real world, maybe it's something from science, maybe it's some abstract fantastical kind of situation, zombie apocalypse or something like that. but you can use mathematics to model that situation. That's really what we're talking about here. Using mathematics as a powerful tool to make sense of the world and to see things, see structures, be able to make predictions, extrapolations, things like that. So for me, that's the value of this practice. It can help connect mathematics to other parts of the world, so maybe it can connect to people's lives. That can be good. Also fantastical situations, like I said, that can also work as well to see the power of mathematics. And mathematics can really be useful in showing the structure of a situation or to help us bring some powerful operations or apparatus from mathematics and then apply it in places. So that's a very valuable one as well when it can fit in. Practice 5 is use appropriate tools strategically. So in this case, we're talking about tools and how they can be used in school mathematics and how tools are important as part of what we would do in mathematics. We don't do mathematics just in our head. We do mathematics with all these tools that are around us and help us make sense of what we're doing, try things out, see things in a new way, and so on. And the tools here refers to physical tools, like a compass or a ruler or pencil, whatever it might be, and also digital tools. So there's new softwares, apps, computers, calculators, that sort of thing. The main point I have about this practice is just that the people are still central. It's the people that are choosing to use a tool. The people or the students are the ones who are strategic about how they're going to use the tool and how they're going to make sense of whatever the tool is showing them or whatever they're doing with the tool. So the person is still the actor, the agent, not the tool. And I also will just emphasize that students need to be the actors and the agents. If you want to be meeting the standard for mathematical practice, the students have to actually choose tools and strategically put them to use. If the teacher is giving the tools and saying, use a calculator on this problem, or if the teacher is saying, use GeoGebra to graph that, whatever's going on, then actually the teacher is the one that's deciding and thinking about which tool is going to make the most sense and give you the most benefit. Students are not making that decision. They're just becoming the operator instead of the decider. So really thinking about students having a chance to think about the tools available to them and make those decisions and then interpret it from what they're seeing. That's really important. Practice 6, attend to precision. This is probably my other favorite mathematical practice in addition to the argumentation and reasoning one, but precision here is really interesting because precision shows up in a lot of ways in mathematics. You can attend to precision of numerical calculations, and that can just be, decimal places, and I'm rounding things, or if I have irrational numbers, thinking about, when the square root of 2 is an exact number and when we've approximated it. Awareness of that is part of this practice. But also there's an awareness of the precision of mathematical communication. When we define something, that's a precise definition. Understanding the implications of your definition, that different definition can change the set of objects that you're talking about. Being aware of that is part of this practice. And also the precision of a claim, like if you make a claim about odd numbers, if you make a claim about certain square numbers, if you make a claim about rectangles or parallelograms, understanding the scope of the claim that you've made. Is it about all parallelograms, or have you made a claim about a certain kind of parallelograms? That awareness is also part of this practice. All right, so practice 7, look for and make use of structure. So this one to me is about mathematical structure, and what I think about for this practice is I think about students or people doing mathematics recognizing that algebraic expressions are not just a collection of symbols strung together, or an equation is not just a longer set of symbols strung together, or a geometric object is not just a shape that you see, but that all of these mathematical objects have structure built in. Parentheses or grouping brackets give you structure. There's an actual piece inside and then that's being squared, or there are two things being added together, or it's a fraction that's being added to another fraction, even if there might be a lot of stuff going on in the numerator and denominator. But just recognizing that I can look at the small little pieces, or I can step back and see chunks, see larger parts of the structure of a mathematical object. Or in geometry, it's not just a rectangle. I can see the sides, I can see the angles, I can imagine the diagonals, I can slice it, I can take it apart, put it back together. Like recognizing that these mathematical objects have a structure inside them and using that flexibly, to me is the real key part of this mathematical structure. And I will say that, because this will help distinguish from the next practice, in practice 7 here about structure, you can see and use the structure within a single mathematical object. a single equation can actually have a structure. You can see something inside, outside, you can see a chunk over here, a chunk over there. You might notice some things that are, similar on the top and the bottom, and noticing the structure that way. But the structure can exist in a single mathematical object. Now, going to practice 8, look for and express regularity in repeated reasoning. This now is a mathematical practice for what you do when you are repeating a process multiple times. If I'm solving an equation, or I'm solving a certain kind of equation, many times over, I've got a whole sheet of, one-step linear equations that I'm solving. Or if I'm going to compute the slope of a line, and then I'm going to compute the slope of another line, and then another line, and I keep computing the slope. When I'm doing something repetitively in mathematics, we don't turn our brain off like a computer. We turn our brain on, and we try to look for patterns across that repetition. And to me, that's what this practice is all about. If I do something multiple times, do I see a pattern emerging? Can I express that pattern? Maybe I compute the slope a bunch of times, and then I express that as, oh wait, there's actually a slope formula that kind of captures that repetition. The thing that I'm doing every time is taking the difference in the vertical change and the difference in the horizontal, and then I can express that pattern. Or whatever it might be, if there's a pattern, can we notice the pattern? Can we express it? So as we do something multiple times, what's going on? Can we see shortcuts? Can we see a formula or something that might encompass the repetition? So this is a fun practice, and it can be one that you can challenge your students where instead of just doing something 20 times, do it 20 times, but keep an eye out for what the pattern is, and can you express or share with one another what you're seeing as that pattern. So this can be an actually pretty fun one, and to me, it's when I'm working with students, it's a way to take something that can be sort of mind-numbing repetition and make it into something more interesting, because we're doing a kind of higher level practice with it. So those are some of my just quick thoughts on the mathematical practices. I went through them all individually, but of course, they are a full set of mathematical practices, and a lot of them interact with one another in lots of ways. So I don't mean to kind of separate them out, but I do think it's helpful, to just think about what each of them means on their own, so that you can then think about how to combine them, or how to do some rich mathematical activity with students that might get several of the practices going all at the same time.